Good morning, class. Today I want to talk about other sorting algorithms. Uh, in particular, I will talk about two specific sorting algorithms. Some of you might have done one of these algorithms in the CS1100 course. The quick sort algorithm and the merge sort algorithm. We will first analyze quicksort. Both these algorithms, although quicksort has a worst case complexity of order theta n squared, um, the average case is log of n to the base 2. As I said, average case analysis. I'll give you an idea of what this is, but we'll show you through examples also. Okay. The other merge sort algorithm is always worst case time complexity algorithm. Nevertheless, quicksort is the more popular algorithm and we will see why. Okay, so let me do the quicksort algorithm. Yeah, so we'll talk about two sorting algorithms, the quicksort and the merge sort algorithm. I want to first discuss the quicksort algorithm. And as I said, these are much faster algorithms than what we have seen earlier, namely the selection, bubble, and insertion sorts, which were all, if you remember, complexity was of the order of theta n squared or order n squared. So let's see how we do this. Why does this algorithm work better? The primary principle that is used in the quicksort or the merge sort algorithm is called the principle of divide and conquer, where what we do is we divide the array into multiple parts, into two parts, just like we did in the context of binary search. But there, for example, in the context of binary search, it's only one part that was processed. Here, on the other hand, we will process both the parts. So let us take an example and let's see how quicksort works. The idea of quicksort is the following. Many of you might have learned it in the CS1100 course. And the idea is just the following. Let's say these are the elements that I have. 94, 18, 6, and 17. What we do is we start off, quicksort and merge sort are both naturally lend themselves to recursion. So I'm going to use recursive algorithms for both of them. So initially, we initialize left here and another pointer I, and we initialize right here and another pointer j. We define middle is assigned, let me not call it middle. Okay, that's what I suppose. Yeah, sorry. Middle is defined as left plus right divided by 2. And we assign a variable called to x. Let me say this array is going from whatever, a of left to right. Okay. Is assigned the value of a of middle. Okay. So I'm going to start with indices from 0 because I've written C programs for all of this. So let's say I started with a of 0 and I went on up to a of 7. The value of middle is, middle becomes 3 initially, and a of middle takes the value of 42. Doesn't matter, you can start with a of 1 also, it's the same thing. So let's say I have, the idea is the following. What we do is the algorithm that I have, there are many varieties of quicksort algorithms that you can choose. So we look at what is the value at middle, and this is the value of x. Then what we do is we move the pointer I until the I'll just tell you in a minute. So what we do is while element a of I is less than x, we do an I plus plus. Similarly, while x is less than a of j, we do a j minus minus. Okay. So what happens? This will remain here. J will remain here. Since this one is greater than this will also remain here. Then what do? We swap the two elements to give us this new array. What happens? We get 44 and 17 exchange. 17 goes here, 44 goes here, and I still have 55, 12, 42, 94, 18, and 6. Now, clearly, if you look at this particular part of the program, you'll find that 17 with respect to 42 is on the right side. Similarly, 42 is on the right side of 40, 44 is on the right side of 42. So what do? I increment the value of I. I decrement the value of j. Again, we find 55 and 6 are out of order with respect to 42. So we repeat this process. And let's see how long we'll repeat this. What we do is, now you come to, so 17, I exchange this, I get 55 here, I get 44 here, I get 12 here, I get 42 here, 94 and 80. Okay. So now these three are in order with respect to 42. What can you say about this? Remember, while a of I less than x. So I is not less than x, so I stop with this pointer here. And a of j, x less than a of j, 42 is less than 18, that's also not true. So this is where I am. And what is interesting about the quicksort is that the element that we chose to divide the array into two parts can itself move. So we have 17, 6, 12, 18, 94, 42, 55, and 44. Then what do? Both I and j are pointing. Then we just go through an exchange of the element with itself so that I gets updated and j gets updated. So what do we get now? Just a minute, I'll just show you what we get. We get 17, 6, the same array. There's no exchange that's happening because I'm exchanging 94 with itself, but the pointer will get updated. 42, 55, and 44. So what will happen now? I'll have I here and j here. So once the two pointers cross, I say, okay, I've looked at the entire array. I still have left pointing here and right pointing here. Now I repeat the same quicksort algorithm between left and I and j and right. Okay. So now what will happen? I have, this will be the middle element. And what you see is 17 is not in the right place with respect to the middle element. So what will happen in this case is that, let us take this part. So I have 17, 6, 12, and 18. I'm going to run quick sort on each one of these parts. So that means what I'm going to do, I'm going to quick sort of left comma I, and I'm going to do quick sort of j comma right. Okay. I repeat this as long as until the size becomes just one element. Okay. So now who is the middle guy? This is the middle guy. Okay. Again, you start with the variable I here, and clearly this is larger than the middle guy, and this is larger than the middle guy. So, and this is also larger than the middle guy until I come over here. So j minus minus, and what will I do? I exchange 6, 17, 12, and 18. So what do we have now? Array again partitioned into two parts, where this part corresponds to one part of the sorted portion, this part corresponds to the other part of the sorted portion. I repeat this again. So this is already sorted because there's only one element, and I have here, this will be the middle value. Let me say this will be 1 and 3, 4 by 2, whatever. And what we are looking at is either this will be the middle value, this, depending upon where your indices start. And again, we'll find that 12 exchanges, and then you'll have 17 and 18, which are in order, and you stop sorting the okay. So this is what the quick sort algorithm is all about. Yeah. So just to make it a little more clear, so when I'm looking at this part of the array, 6 and 17 exchanged is fine. This has become already sorted. It has only one element. Then you have three elements here. Suppose this is the middle element. What will happen? This is your I and this is your J. And what will happen? It will come and stop here. Then what will happen? 17 and 12 will get exchanged. And then this was a single element, so it's already sorted. 17 and 18. Process will be repeated again, and eventually you'll find that 17 and 18 are in single cells, and it is done. Okay, so this is what the quicksort algorithm is. Let us quickly sketch the outline of this algorithm. I have used an array V in my program, not for any specific reason, but just that I don't want to change the variable name here so that I don't make mistakes. Let's say I have int v, which is an array of uh, v is an array of integers, and we of course pass the values of left and right, which are of type integer, right, which are both of type integer. And what do? We start with this. I have two variables, int I, which point to the left and initially to the right, left and right portions of the array. I assign I to left, I assign j to right, and we assign a variable we call int x, which is assigned the value of b of left plus right to the middle element. Okay. By the way, this pivot element can also be chosen as the first element. Some versions also choose it as the first element. Then I repeat this block. So that means what? It's a repeat until block. That means everything is going to be executed at least once within the block. So what do? While b of I less than x, do I to I plus 1. And while x less than v of j, do j minus, j is assigned the value j minus 1. If I is less than or equal to j, then I swap. This is just to take care of the last case which I showed there where 94 was sitting by itself. It will also take care of that sentinel problem that we have. J, so the pointers get updated. I is assigned the value I plus 1. J is assigned the value j minus 1. End if, and we repeat this until I is less than or equal to j, as long as uh, I becomes less than or equal to j, or j becomes greater than I. Okay, that means the pointers are crossing. If left is less than j, then we quick sort on the new portion. What is the new portion now? It is from v, left, and I, because the two pointers have crossed, and we do a quick sort. If I is yeah, sorry, this should be, I mistook this. This should be j over here, because j is the pointer which is coming from the right, and quick sort if, similarly, if one moment, if I is less than right, then quick sort. Basically what this tells us is that j is in between the leftmost sentinel, and that is the array is being divided into two parts, where up till j you have an unsorted portion, and from I to the right you have an unsorted portion, and that's what we are trying to do. B of I comma right. Okay, and this is all the quicksort algorithm is all about. Let us do an analysis of this algorithm.